Bismillahirrahmanirrahim. Alhamdulillahirabbil alamin. Wassalatu wassalamu ala asyrafil sayyidina wal mursalin wa ala alihi wa sahbihi ajma'in. Subhanaka la ilma lana illa ma 'allamtana innaka antal alimul hakim. Rabbi shrah li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Wala haula wala quwwata illa billahil 'aliyyil 'azim. Allahumma shalli ala sayyidina Muhammad wa ala alihi wa sahbihi ajma'in. Assalamualaikum warahmatullahi. How are you today? Can you hear me?
Good, I'm good. I'm good.
Yeah. Okay. So okay, as we know, microprocessor can execute multiple process at the same time. So what we call is multitasking, right? So I want to ask you, is it really multi-process in the same time? Is it true? The process is on the same time. Anyone? Microprocessor can process multiple process, right, at the same time, what we call as a multitasking, right? So my question is it really at the same time? Are you hear me? Can somebody ask my question? Answer my question? Okay, so you answer in chat box. Alright, okay. So I read here. I can see here. Okay. So maybe yes and maybe not. Alright. Okay. Okay. So maybe it is true if we call if we state like this multiple process at a 1 second or millisecond, okay, or microprocessor can multiple process at a 1 microsecond, right? So maybe how about nanosecond and picosecond? Right, the statement cannot sometimes cannot be true. So actually we have a way to do at the same really same time, what we call as parallel. So multiple microprocessor, okay, work together to process multiple process ataupun multiple program at the same time, really same time. Okay, so what we a multi-core. The multi-core is a part of parallel. Alright. Okay. So what we learned before this in chapter 1, processing, interprocessing communication, or multi-process in Unix, right? So there are a lot of process to be executed by microprocessor. Okay, so we gonna go through to this chapter 8. Let me share my screen. All right. Okay. Can you see my slide? This slide I took from my friend Sir Ahmad Fidaus. So he teach parallel processing. Okay. So let's begin. Let me introduce you to parallel computing. Okay. The past decade has seen tremendous advance in microprocessor technology. Clock rates of processor have increased from about 40 megahertz. You can see there in 1998, the microprocessor name MIPS, MIPS, okay, to over increased to over 2.0 gigahertz, 2 gigahertz in 2002, which is a Pentium 4. Okay. At the same time, processors are now capable of executing multiple instructions in the same cycle. The correct word is the same cycle. The average number of cycle per instruction, or CPI, of high-end processors has improved by roughly an order of magnitude over the past 10 years. Okay. This translates to an increase in the peak floating point operation execution rate, or what we call floating point operation per second, or acronym for FLOPS, flops, right? Of several orders of magnitude. A variety of other issues have also become important over the same period. Perhaps the most prominent of this is the ability of the memory system to feed data to the processor at the required rate. Significant innovation in architecture and software have addressed the elevation of bottlenecks posed by the data pass and the memory. So, any question? Are you clear? Are you clear? All right, good. So let's continue. Where's my PowerPoint? There. The role of concurrency accelerating computing element has been recognized for several decades. However, their role in providing multiplicity of data paths, increased access to elements, which is both memory and disk, and then scalable performance and lower cost in reflected in the wide variety of application of parallel computing. Desktop machines, engineering workstation, and computer servers with 2, 4, or even 8 processors connected together are becoming common platform for design application. Large-scale application in science and engineering rely on larger configuration of parallel computers, often comprising hundreds of processors. Data-intensive platforms such as database and web server and applications such as transaction processing and data mining often use cluster of workstations that provide high aggregate disk bandwidth. Application in graphic and visualization use multiple rendering pipes and processing elements to compute and render realistic environments with millions of polygons in real time. Applications requiring high availability rely on parallel and distributed platform for redundancy It is therefore extremely important from the point of view of cost, performance, and application requirement to understand the principal tools and techniques for programming the wide variety of parallel platform currently available. Okay. So this is how clear tak? Tak nampak slide ya? Okay. So okay lah tu, kalau nampak slide pertama je betul lah. Okay. So we move on to the next slide. Kan? Dah warning dah. Stream current bit rate is lower than recommended bit rate. Sudah. Kan, good connection. Tadi excellent. Right. Okay, continue. Continue, muka saya tak nampak kan? Share audio kot. Share audio buat apa? Mana ada audio dalam ni? Okay. Where is it? Okay. If you can see here, okay, it look like a downgrade. The microprocessor has been downgraded. Actually, is not, because the latest technology using a parallel, right? Parallel processing. There is multi-core here. There, if you can see there, in 2016, Intel Core i7 there, right? The clock rate is 3.2 gigahertz, which is lower than 2005's microprocessor. Intel Pentium 4, 3.8 gigahertz, right? Okay. So number of core, you can see over a decade of extreme addition innovation in Intel. Okay, single core, dual core, quad core, 6 core, 8 core, 10 core. Okay, next, we're moving to motivating parallelism. Okay. Development of parallel software has traditionally been thought of as time and effort intensive. This can be largely attributed to the inherent complexity of specifying and coordinating concurrent tasks, a lack of portable algorithms, standardizers, environment, and software development toolkits. When viewed in the context of the brisk rate of development of microprocessor, one is tempted to question the need for devoting significant effort towards exploiting parallelism as a means of accelerating application. After all, if it takes 2 years to develop a parallel application during which time the underlying hardware and or software some unmistakable trend in hardware design, which indicate that uniprocessor or implicitly parallel. So this architecture may not be able to sustain the rate of realizable performance increment in the future. Okay, this is a result of lack of implicit parallelism as well as other bottlenecks such as the data path and the memory. At the same time, standardized hardware interfaces have reduced the turnaround time from the development of a microprocessor to a parallel machine based on the microprocessor. Furthermore, considerable progress has been made in standardization of programming environment to ensure a longer life cycle for parallel application. So all of this present compelling argument in favor of parallel computing platform. Okay. So there is a more law number of transistor flops, okay, floating operation per second. So who is law? Who is law? Who is more? More laws. Who is more? More is Gordon Moore. Okay, made the following simple observation in 1965. So what he said, the complexity for minimum component cost has increased at the rate of roughly a factor of 2 per year. Uh, 2 per year. Certainly over the short term, this rate can be expected to continue, if not to increase over the longer term. The rate of increase is a bit more uncertain, although there is no reason to believe it will not remain nearly constant for at least 10 years. That means by 1975, because his statement in 1965, 10 years later, 1975, the number of components per integrated circuit for minimum cost will be 65,000. Okay, his reasoning was based on an empirical log linear relationship between device complexity and time observed over 3 data points. He used this to justify that by 1975, devices with as many as 65,000 components would become feasible on a single silicon chip, occupying an area of only about 1/4 on a square inch. This projection turned out to be accurate with the fabrication of a 16K CCD memory with about 65,000 components in 1975. In a subsequent paper in 1975, Moore attributed the log linear relationships to exponential behavior to die sizes, final minimum dimension, and circuit and device cleverness. He went on to state that. Okay. The second one is the memory disk speed argument. The overall speed of computation is determined not just by the speed of the processor, but also by the ability of the memory system to feed data to it, while clock rates of high-end processors have increased to roughly 40% per year over the past decade. DRAM access time have only improved at the rate of roughly 10% per year over the interval. Coupled with increase in instruction executed per clock cycle, this gap between processor speed and memory present a tremendous performance bottleneck. This growing mismatch between processor speed and DRAM latency is typically bridged by a hierarchical successively faster memory devices called cache. So there is cache begin that rely on locality of data reference to deliver higher memory system performance. In addition to the latency, the next effective bandwidth between DRAM and the processor pose as a problem for sustained computations rates. The overall performance of the memory system is determined by the fraction of the total memory request that can be certified by the cache. Memory system performance is addressed in greater detail later. Okay, parallel platform typically yield better memory system performance because they provide larger aggregate cache, higher aggregate bandwidth to the memory, both typically linear in the number of processors. Furthermore, the principles that are at the heart of parallel algorithm, namely locality of data reference, also and themselves to cache-friendly serial algorithm. This argument can be extended to this, where parallel platform can be used to achieve high aggregate bandwidth in secondary storage. Here, parallel algorithm yield insight into the development of out of core, okay, computations. In the same Indeed, some of the faster growing application area of parallel computing in data server, such as database server, web server, thus rely not so much on their high aggregate computation rates, but rather on the ability to pump data out at a faster rate. The next is the data communication argument. So that's why the parallelism occur. To motivate parallelism, the other factor is data communication argument. As the networking infrastructure evolved, the vision of using the internet as one larger heterogeneous parallel distributed computing environment has begun to take shape. Many applications lend themselves naturally to such computing paradigm. Some of the most impressive applications of massively parallel computing have been in the context of wide area distributed platform. Right? In many applications, they are constrained on the location of data or resource across the internet. An example of such an application is mining of larger commercial data set distributed over a relatively low bandwidth bottleneck. In such application, even if the computing power is available to accomplish the required task without resorting to parallel computing, if it is feasible to collect the data at a central location. In this case, the motivation for parallelism comes not just from the need for computing resource, but also from the infeasibility or undesirability of alternate for centralized approach. So nowadays we have big data, right? From data mining, we have a big data today. So there is one of application of parallel processing. So any question? Ready for the next slide? Last topic, last topic for today. So we gonna go to Not okay. You have class today? Ready? Yeah, ready. So we're gonna go to scope of parallel computing. Scope of parallel computing. Tak boleh jawab ni. Alright. Okay. So can we see here four scope? Okay, application in engineering and design, scientific application, commercial application, and last is application in computer system. Okay, parallel computing has made a tremendous impact on a variety areas ranging from computational simulation for scientific and engineering application to commercial application in data mining and transaction processing. Okay. The cost benefits of parallelism coupled with the performance requirement of application present compelling argument in favor of parallel computing. We present a small sample of diverse applications of parallel computing. First, application engineering and design. Parallel computing has traditionally been employed with great success in the design to airfoils, optimizing lift drag stability, internal combustion engines, optimizing change distribution, burns, high-speed circuit, layouts for delays and capacitive and inductive effect, and structure, optimizing structure integrity, design parameters, cost, etc. Among others, more recently design of microelectromechanical and nanoelectromechanical system has attracted significant attention. While most applications in engineering and design pose problem of multiple spatial and temporal scales and couple these physical phenomena. In this case, all design these problems are particularly acute. Here we often deal with a mix of quantum phenomena, molecular dynamics, and stochastic and continuum model with physical process such as conduction, convection, radiation, structure mechanics, all in a single system. So there is a one of scope of parallel computer. The second scope, scientific application. The past few years have seen a revolution in high performance scientific computing application. The sequencing of human genome by International Human Genome Sequencing Consortium and Celera, for example, has opened a exciting new frontier in bioinformatics. Functional and structural characterization of genes and proteins hold the promise of understanding and fundamentally influencing biological process. The next is commercial application. Okay, with the widespread use of the web and associated static and dynamic content, there is increased emphasis on cost-effective server capable of providing scalable performance. Parallel platform ranging from multiprocessor to Linux cluster are frequently used as web as database server. For instance, on heavy volume days, large brokerage house on Wall Street, for example, handle hundreds of thousands of simultaneous user sessions and millions of orders. Platforms such as IBM SP supercomputer and Sun Ultra HPC servers this this business critical site. Okay, while not highly visible, some of the largest supercomputer networking houses on Wall Street. The last one is application in computer system. As computer system become more pervasive and computation spreads over the computer, parallel processing issues become ingrained into a variety of applications. In computer security, intrusion detection is an outstanding challenge. In the case of network intrusion detection, data is collected as distributed site and must be analyzed rapidly for signaling intrusion. Then invisibility of collecting this data of a central location for analysis require effective parallel and distributed algorithm. In the area of cryptography, some of the most spectacular applications of internet-based parallel computing have focused on factoring extremely large integer. So for more detail, you can read on the textbook. Alright. Okay. Oh, slide dah tak nampak. Alamak, tadi slide tak nampak. Ini slide dah. Sekali lagi. Ini adalah scope of parallel computing. Application engineering and design, scientific application, commercial application in computer system. Right? So example dia. Ada satu lagi benda yang dia orang tak letak untuk movie industry. Kan? Movie industry dia tak letak sini. Application lah. Kan? Contoh dia dalam cerita alamak, cerita apa ah? Armageddon. Armageddon. Siapa pernah tengok Armageddon? Pernah tengok cerita Armageddon? Bruce Willis. Kan? Waktu dia orang dekat spaceship tu kan, bila nak lalu celahan meteor tu kan, komputer buat kerja nak analyze incoming sepihan-sepihan tu kan. Tu sebenarnya pakai parallel processing lah tu. Satu processor memang tak cukup. Kan? Okay. So that's all for today. Any question? Ada nak dengar tak? Saya risau tak dengar. Kena repeat balik ini. Dalam setengah jam ni. Okay. Okay, nanti tengok, boleh tengok balik dekat no question. Okay. That's all for today. Thank you for your time. So next week final chapter lah. Kan? Next week final chapter. Minggu ni minggu ke? This week week 12. Okay, slide ada kat saya, ada kat desktop saya. Nanti saya letak kat kasturi. Boleh saya letak kat kasturi. Right. Lain-lain. So minggu ni minggu 12, next week 13. Lepas tu 14 kan, ada 2 minggu lagi. Then next week kita pergi final chapter. Tak apa, kita nak sembang, saya tutup live dulu lah. Saya tutup live dulu, kita sembang. Stop streaming, stop live stream. Alright. Saya stop streaming ya. Jumpa lagi semua orang. Assalamualaikum.